longer talk that tends to be quite long, right? Much longer than scheduled because people will stop. So don't worry about if it goes on. Just feel free to. I haven't cleared this with Dima, but interrupt him and tell him what you think. And then today we've got 2 short talks on more specialized sort of issues, perhaps. And then in the afternoon, what we've been doing is just try to work, maybe talk to each other, all that sort of stuff. And then we reconvened at 4 o'clock for a free streaming coffee discussion that has ranged from, I think, last week's the ludicrous to the slightly less ludicrous. I think on Friday we actually talked a little bit about serious science, but the first day I think that was not the case. So there you go. So what about the whole week? Thursday afternoon we are not planning to have anything scheduled, so that's the afternoon to take off, perhaps if you want to go around and see Stockholm, for those of you that weren't here last week, but for those of you that were here during the weekend, you will be working on Thursday. The new updated program, because it changes a little bit as we go along. Lars has printed it out, it's down there. And that's pretty much, no, one more thing. I think we're planning to have some sort of social event thing after Luciano's talk on Wednesday. But I also don't think we quite know what it is yet. Right?
Depends on weather.
Because it depends a little bit on how the weather develops. We were thinking of maybe doing something outside, but it depends on whether it's snowing or not. So, all right. So maybe we should start. Someone said the Russians are coming, and I should just tell you, I'm very pleased that the Russians are coming and have come. My mother would not be so happy. She belongs to this generation from 1950s when this statement, the Russians are coming, is very bad. But I think in our community we're quite glad that they actually did. So there you go. Sorry about that. But actually I should explain that in Sweden the statement the Russians are coming goes back to the 1700s when Sweden essentially lost our entire north of Europe to the Russians, the Poles, and pretty much everybody that wanted to take what we didn't deserve anyway. So it's an old thing. Anyway.
Yeah, thank you very much for the introduction, and don't be afraid of me. I will work in 1 week. It's well.
Sorry, Dima, you say don't be afraid of you, and look at that list.
Yeah. It's a pleasure to be here. Thank you very much for the invitation. Well, I will try to discuss transport properties of neutron stars. The subject is actually huge, and I like to be asked during the talk, so please attack me and try to prove that I am wrong. That's the best thing to do. So the map is here, the map of my talk. First I will describe some general properties of kinetical theory of the neutron star crust, then physical conditions, and then I will describe point by point transport properties produced by different particles in the crust, radiative thermal conductivity, electron transport in the magnetic field, then ion transport, neutron transport, and then finally, if we survive, there will be a brief discussion of applications and conclusions. Okay. So, this will be a review talk about some things were done in collaboration with several co-authors. I like them very much. This collaboration was very inspiring for me, so their names are here. And I will just say a few words about the neutron star crust. I am sure that it was discussed here. So I will discuss the transport properties of the crust, which extends from the atmosphere to the liquid core of the neutron star, and which consists of several very different layers. First, the atmosphere. Then, if we go deeper and deeper, there will be liquid ocean of ions. Then there will be the crust itself, ions will crystallize into Coulomb crystal, and this will be the outer crust up to the neutron point. Then neutrons will appear in the inner crust, and perhaps there will be a mantle of a liquid crystal which consists of nuclei with funny faces, probably discussed by Professor Watanabe at this workshop. So we have, well, huge range of physical conditions. The density varies from the surface, where the density is around 1 gram per centimeter cubic, to the core densities. Nuclear matter densities around 1/2 nuclear matter densities around 10 to the 14 grams per centimeter cubic. So the contrast of densities is huge. The contrast of temperatures, the difference of temperatures, which should be considered here, is also huge. So kinetical properties of these layers, they constitute a big field, almost not explored. Okay, so if we discuss transport properties of neutron star crust, we should speak about different transport carriers, different transport coefficients. First, we should study thermal conductivity of the matter. Then charge transport gives us electric conductivity or electric resistivity. Heat and charge transport gives us thermal power, which can also be important for generation of magnetic fields. Then momentum transport produces shear and bulk viscosity of the matter. And then there are diffusion coefficients of different particles, which are also important to study, for instance, well, after burst relaxation in the surface layers of neutron stars. So we should discuss all these transport coefficients. Well, what about carriers of charge, heat, and so on? There are different carriers there. In the very surface layers of neutron stars, well, the heat is transported by photons. There is radiative thermal conductivity. Then deeper, the heat and charge is mainly transported by electrons. There are electron transport properties, and the electrons may scatter off ions, phonons, electrons, and so on. Well, there are many different mechanisms of electron scattering. But then there are ions. Ions are heavy, and it seems that they do not participate in the transport. But this is, well, the wrong idea. They do. So the ions participate into the thermal conductivity, for instance, across the magnetic field, and there are many mechanisms of ion scattering as well. And finally, there are neutrons in the inner crust of the neutron star, and neutrons, they can also produce thermal conductivity, which can also be important. Okay, well, just to survive, I will possibly miss this slide, and we'll go to the next one. Well, about main regulators. What regulates transport properties of neutron star matter? These properties are regulated by many things. First of all, by density and temperature. Then by the composition of the matter. It is brown state crust or accreted crust. Transport properties will be different. And then, for instance, ion-ion correlations are very important for calculating the electron transport properties, because ions are very good scatterers of electrons. So then, certainly at the magnetic fields, they will modify all transport properties. Then superfluidity of neutrons, as I'm sure that Sanjay Reddy will discuss this, in the inner crust will produce a very fine effect. It will produce quite a huge thermal conductivity. Then properties of atomic nuclei and nuclear structures. They are also important for some transport properties of the matter. Then about techniques, how to calculate all these transport properties. There are different techniques depending on the situation because physical conditions are very different. Well, many transport coefficients are calculated using the Boltzmann equation, linearizing this Boltzmann equation and solving the linearized equation by different methods, variational method. Well, there are some exact solutions, polynomial expansions and so on. If we are speaking of transport properties of ions in strongly coupled Coulomb liquid, then molecular dynamic simulations are very important for calculating some transport properties. Well, all these techniques are taken from different branches of terrestrial physics, from solid-state physics, and well, there is large similarity between the situations which we have in neutron stars and in solid-state physics. But in some cases, this interference with solid-state physics seems well harmful from my point of view. One can obtain wrong results which are invalid in the neutron star cross just taking the methods of solid-state physics, and I will discuss this. Well, there is physics of condensed matter, for instance, this wonderful textbook by Bain and Pesek about Landau thermodynamic theory, where transport properties in the frames of the thermal-liquid theory are described. Then there is plasma physics, where a lot of problems which can be applied to neutron star crust have been solved, and so on. So there are the techniques, there are the methods, and this is a complicated business. Well, about history. Well, to my mind, the history of this business started in the 1940s by the works of three prominent scientists, Marshak, Mestel, and Lee, who calculated the electron thermal conductivity in the strongly degenerate relativistic electron gas due to scattering of electrons of atomic nuclei of ions, treating ions as well just almost perfect gas, just Coulomb scattering, and that's all. Well, then in 1960s there were several very good papers published by Hubbard and Lampe. They were started by Martin Lampe, who calculated the electric thermal conductivity of dense matter, not applying the results directly to neutron stars, but works. They were really good. They calculated the thermal conductivity for mildly degenerate electrons, considered many cases, published tables which are used even now. But then, after the advent of neutron star physics, new generation of scientists came into scene and started, it was a flow of papers devoted to transport properties of neutron star crust. There was huge activity initiated by Vittorio Canuto, and many scientists participated into these activities in 1970s, which actually attracted my attention to this problem because I was fascinated reading their papers. I was fascinated by two things. First, by the amount of energy which was input into the problem, and second, by the amount of points in which my university education disagreed. So, I was forced to publish several papers with Vladimir and by myself devoted to the conductivity of electron gas. And then there was a wonderful paper by Flores and Ita in 1976. It was just the start of systematic study of all transport properties in the crust. And later, Naoki Ita and collaborators did a very good job calculating different transport properties, electrical conductivity, thermal conductivity, viscosity, and so on. And then there were many publications which I just cannot list. Okay. Well, and the final point of the introduction is the role of physical kinetics in the neutron star physics. And this is like this. If you consider this Nobel Prize construction devoted to neutron stars as His Majesty the King, then physical kinetics is here. It's grabbing flows. Because it is non-profitable business. Students refuse to solve kinetical problems because they're saying, a lot of physics, it is too complicated. Researchers refuse to solve these problems because, there is no profit in this. Everyone needs kinetical properties, but no one wants to calculate them. Okay? So, I have finished the introduction, and now about physical conditions. So, this is the temperature density diagram of the neutron star crust. I'm sorry for carbon matter, but it doesn't matter. For all chemical compositions, the situation is nearly the same. This is logarithm of density of the matter, logarithm of temperature, and different lines show if we go from the left up corner to the right down corner, we will first see this line, electron degeneracy. Electrons become degenerate and relativistic here. And then the ions above these lines, they constitute Boltzmann gas, but below this line they constitute strongly coupled ion liquid, which finally becomes solid. So the inner crust is mostly solid. Initially, the strongly coupled Coulomb system is classical. One can consider this motion of ions neglecting quantum effects, but at low temperatures and high densities, when the temperature falls down below the so-called ion plasma temperature, which is determined by the ion plasma frequency, omega p, then this system becomes quantum. You cannot neglect quantum effects. So the inner crust is mainly quantum system. this show, well, how the ions behave. When the ions constitute the Boltzmann gas, they are moving freely in a potential which is created by other particles, but this potential is minor. It does not affect strongly their motion. When the ions constitute strongly coupled classical system, they move in potential wells, self-consistent potential wells created by all these plasma particles. But their motion is classical because we can neglect the structure, quantum structure of energy levels. The temperature is high. But when the temperature is low, lower than the ion plasma temperature, then the structure of these levels, quantum levels in the potential wells, becomes important, and we cannot treat the ions as classical particles. We should consider them according to quantum mechanical theory. Well, I will probably to save time. Well, the third part of my talk is radiative thermal conductivity in the very surface layers of neutron stars. I mean here, well, the layers where the electrons are mainly non-degenerate, and in these layers heat is conducted by photons, not by electrons. So one should consider this. So we have a lot of different problems here, because when we calculate the radiative thermal conductivity, we should take into account different mechanisms of photon interaction with medium, that's with decreasing temperature. There will be electron scattering, then free transitions, bound free transitions, bound transitions, and so on. There are many problems created by non-ideality of electron gas, by the problems of pressure ionization and atomic structure of high densities, because at high densities the atomic structure start to disappear due to this electron pressure ionization effect. And well, actually this problem can be taken into account, but only in a model way. There is no model independent theory in this case. Then this is absolutely unsolved problem. If we go inside, when the density becomes so high that the temperature starts to be lower than the electron plasma frequency, kT is lower than h omega ppe. Omega ppe is the electron plasma frequency. And then no photons can propagate in this medium, so there should be cutoff of the radiative conductivity, which has not been considered properly so far. In addition, there appears some new mechanism of thermal conductivity due to longitudinal plasmas. Longitudinal plasmas, this effect was not considered also. And moreover, if we have a magnetized plasma, then there appears there the window frequency, low frequencies in which the photons can propagate through the plasma. In a magnetized plasma, it is possible, and this is the new mechanism for the thermal conductivity, which has not been considered in the literature at all. Okay, then effects of the magnetic field on the radiative thermal conductivity of rarefied, sufficiently rarefied plasma. These effects were studied, And in this case, if we have a magnetized plasma, a plasma in a magnetic field, and if we consider photon thermal conductivity, it becomes anisotropic. There appear two different thermal conductivities along the magnetic field and across the magnetic field, and the effect of the magnetic field is mainly regulated by one parameter, h omega b, where omega b is the electron cyclotron frequency over kT. If this parameter is small, then the magnetic effect is negligible, and we can consider the situation is close to the situation without the magnetic field. But if this parameter is large, then the thermal conductivity along and across the magnetic field becomes enhanced. The enhancement is proportional to omega b squared, is proportional to the squared magnetic field. And this is typical situation. This is h omega b over kT, and this is the ratio of the thermal conductivity and the thermal conductivity without the magnetic field. For Thomson scattering, electron scattering, perpendicular and along the magnetic field, both conductivities grow up and becomes very high. The effect, it is because in a very strong magnetic field there appear two waves in plasma, ordinary and extraordinary, and photons of extraordinary wave. They have very long mean-free path because they weakly interact with medium. This mean-free path increases with the increasing of the magnetic field as omega b over omega squared, and this produces the effect. So this is very old stuff. The theory was, well, the theory, we wrote these equations with George Pavlov, and George Pavlov was not a successful American observer, but a very successful Soviet theorist. Wow. And now I'm coming to the main subject of my talk, electron thermal conductivity. It is most important. So if we have this, well, electron thermal conductivity, we can generally consider three cases. The first case, non-degenerate electrons, very surface layers of neutron stars. This case was done very long ago in plasma physics. There was some paper by Draginsky published in Soviet Physics of Experimental and Theoretical Physics. Initially the paper was not accepted because the main point of the referee was that it was not a practical theory. The theory was developed, but there were no one systems to which this theory could be applied, so it should not be published. It was done in a magnetic field, by the way, and Draginsky considered not only transport by electrons, but transport by ions as well. So this, well, complicated business was huge work. But then, if electrons are mildly degenerate near this electron degeneracy line, then there is no exact theory, and so but there are some interpolations which were produced by Sasha Platichin, and I will discuss them later. But when electrons are strongly degenerate, so we will discuss this case. We will discuss the case of strongly degenerate electrons. Well, the electrons are degenerate through the whole crust, except for the various surface layers. Ooh. Yeah. No one asks questions, but I am moving so slowly. But I can be stopped any minute, anybody.
You'll also be chairperson of this session, so you can negotiate it yourself.
Okay.
We can just take a break for lunch and come back to work.
Wow. No. Not a good idea. I would like to survive. And what will you do with my dead body?
Buy cargo books.
Transportation. My body transport will be a problem. Okay, if the electrons are complicated, degenerate, then the distribution is the Fermi-Dirac distribution given by this expression. The dependence of the Fermi-Dirac distribution function on the energy is given by this line. We have this is chemical potential and this is Fermi C. Fermi C of electrons contributes to the equation of state but does not contribute to transport. And we have this thermal width of the Fermi level and all transport properties of degenerate electrons as well as degenerate neutrons and all degenerate particles, they are determined by the distribution function here. Here this distribution function is distorted and the relaxation produces the transport. So division of responsibilities. Fermi C produces the pressure and the thermal width of the Fermi level. Miserable numbers of electrons, they contribute into the transport. Okay. Well, they are the equations, which I will try to skip. This is the linearized Boltzmann equation for the electron distribution function with some collision integral. Let us assume that the plasma is immersed into the valve. There are weak temperature gradients, chemical potential gradients, and weak electric fields applied. These gradients and the electric field will produce currents in the plasma. They will produce the electric current and the thermal current. The distribution function of electrons will be disturbed. It will be given by two terms. The equilibrium distribution function plus perturbation near the Fermi surface. And this perturbation will initiate these currents. This is electric current, this is I'm sorry. This is the thermal current, and these currents will be proportional to the electric field. This is actually not the electric field, but some generalized electric field which is created by the electric field itself plus some effective electric field which is produced by the gradient of chemical potential and gradient of temperature. And this temperature gradient. And the same with the thermal current, it will be proportional to the electric field and a gradient of temperature. And here we have three kinetic coefficients. Sigma is electric thermal conductivity, alpha T, and tilde kappa, two other coefficients. The coefficient here is equal to coefficient here because of Gonzaga principle. And this is pretty inconvenient and never used in applications. because it is better to solve and to express the transport properties in terms of this electric field. If we solve for the electric field, we will write down the transport relations in this form. The electric field is proportional to the electric current and temperature gradient, and the thermal flux is proportional to the electric current and temperature gradient. And here we have again three coefficients, but they are practical. One of them is the same. This is the electric conductivity, or inverse quantity electric resistivity of the matter. The second one, kappa, is the thermal conductivity, and the third one, QT, is thermal power. So we should calculate generally all of them. And the calculations show that the electrical and thermal conductivities, they are positive. They cannot change sign. But the thermal power, it is a delicate thing. It can change sign depending on many things. Okay, the electric conductivity and thermal conductivity can be expressed in the Drude form through the effective relaxation times tau sigma for the electric conductivity and tau kappa for the thermal conductivity. These relaxation times are generally different. They are not equal, but at high temperatures they are more or less the same. Well, we can write down that each relaxation time is can be expressed as inverse effective collision frequency, written as 1 over nu, where nu is the collision frequency of electrons. And again, if there are different mechanisms of electron scattering, we can calculate this collision frequency as a sum of different collision frequencies.
We ask you, when you say high temperature in this context, what does it mean? We say high temperature.
High temperatures mean here, in this context, it means that, the electron scattering should be almost elastic. So the energy transfer in one scattering event should be much smaller than kT. And if we translate into numbers, this means that the temperature should be higher or order of the ion plasma temperature, or the quantum temperature. It is. And if they're equal, then we will have this famous Wiedemann-Franz rule, which relates the electric and thermal conductivity one relaxation time, and one should not calculate, these quantities twice. It is sufficient to calculate this relaxation time, and we will know both quantities immediately. Okay. Then the main electron scattering mechanism is electron-ion scattering. Scattering of electrons by ions. And if we decrease temperature, this scattering manifests itself, it is called by different names. At high temperatures it is just direct Coulomb scattering by ions. At lower temperature it is scattering by ion charge fluctuations in strongly coupled Coulomb systems. And at very small temperatures, when ion crystallize, this is scattering by phonons. And it is quite evident that at very low temperatures, when the number of phonons is strongly reduced by quantum effects, this scattering will be inefficient. This is electron. This is just for the case when the scattering is nearly elastic. there is some relaxation time approximation in which one can easily calculate this relaxation time through the effective collision frequency as the number of scatterers ions times the velocity of the electrons and times the transport scattering cross-section, and this is Coulomb scattering cross-section at high temperatures, and we immediately obtain this result. Where it is? The transport scattering cross-section can be expressed like this. Z is charge of ions, and lambda is so-called Coulomb logarithm. So this Coulomb logarithm can be expressed as some integral, and if we do nothing to change direct Coulomb interaction, this Coulomb logarithm will become divergent. So this is, in the theory, it is, well, big number. But tiny effects of screening of plasma interactions will make it, well, finite. So this is the problem. And when you calculate this Coulomb logarithm, this is complicated business, and, well, I will not go into the details. You should take into account electron screening, ion, deuterium ion correlations, finite sizes of atomic nuclei at high densities, phonon descriptions at low temperatures, multi-phonon scattering process, and, well, non-bond corrections. And in general case, Coulomb logarithms for heat and charge conduction, they are different. And at low temperatures, Coulomb logarithm become small, and there's actually have no meaning of real Coulomb logarithm. They are small quantities, they can be called generalized Coulomb logarithms. But if we are speaking of quite, well, high temperatures, this is very simple. This relaxation time is a very simple, well, thing. Estimate is written here. This is just the atomic time. Well, if you have, for instance, a hydrogen atom, then there is some atomic time associated with the rotation of an electron around the atom, 10 to the minus 17 seconds. Well, this is just the Bohr time, 10 to the minus 17 or something like this, corrected by Z, the charge number. Okay. Well, finally, well, a few figures. Then this figure shows the dependence of the electrothermal conductivity versus density at a given temperature of the matter for different compositions. This is hydrogen plasma, this is iron plasma. The higher Z, the atomic number, the lower the conductivity, which is quite natural because this is Coulomb scattering, and if we have high charge ions, they scatter electrons more efficiently, so the conductivity should be lower. And this is the dependence of the conductivity on density for iron matter, but for different temperatures. And you can see that this dependence is not monotonic because of quantum effects. And this is the dependence of the electric conductivity. Just for example, the same situation will appear in shear viscosity or thermal conductivity. The dependence on temperature for the density of 10 to the 8 grams per centimeter cubic for iron matter, and this is, well, the melting temperature. And at the melting temperature, well, the calculations show that there is no conductivity jump, or almost no conductivity jump. And this result seems to be robust. You can consider melting into BCC lattice, into thesis lattice, into other Coulomb lattices, and the result is independent actually on the type of the lattice, and the result is actually independent on the real state of the matter. If it is liquid or solid, it does not matter. This is in sharp contrast with solid state physics, where we have jump of the electric conductivity or thermal conductivity. These jumps, they are, well, investigated, they are real, but here the situation is physically quite different.
Why do you assume the thermal conductivity is the same for the liquid and solid?
I do not assume, I have calculated.
Do you have a quantum theory for the liquid?
Quantum theory for the liquid, no. But, well, what we did, we just calculated for classical liquid and for quantum solid. And we shifted artificially the melting point. And if we shifted the melting point to in the region of high temperatures, then we have better match between the results. So it seems that we do not have theory for the liquid, but if we had, well, it would show us, well, the same. We artificially shifted this, well, melting temperature in huge, well, ranges. And it was one and the same graph.
You have a prescription for the static structure factor for the
Yeah.
liquid,
Yeah.
where you...
Yeah. With this prescription, we calculated, well, we calculated these conductivities, and we obtained no jumps. Almost no jumps, I would say. There are some jumps, but they are really well minor.
Your prescription gives a small jump. Are you very, very confident of that prescription?
Well, this is written here. Our prescription was criticized. It was criticized by Naukita and by Beligo and Gupta recently. And their criticism was just because in the solid state physics it is not true. But this can be formalized. Well, there are theories which allow to understand how to go from the conditions of solid state, ordinary solid state physics to the astrophysical conditions. These conditions are quite different because in the solid state physics, Coulomb forces are most important one. In a crystal, in terrestrial crystal, Coulomb forces are much stronger than the forces which are produced by the generator electrons, because it is confined lattice. In astrophysical conditions, it is quite well different, because Coulomb forces are minor, and the pressure, the generate electrons, they produce the main effect. So the situation, well, if we, in photoresterral matter, we will have the jumps, when we will increase the density from terrestrial matter densities to the densities at which, well, the electron gas becomes almost ideal and uniform, we will have this result. This is not done, but this can be done. This is not a problem because in the solid state physics, well, there are some theories which allow one to do this, but this is not done.
So basically, as you go to high density, a high
Yeah.
degree of ionization,
Yeah,
this first order phase transition between solid and liquid gets weaker and weaker,
yeah,
and it almost behaves like a crossover.
yeah.
So but it seems to happen over a rather large range here, right, between almost 1 order of magnitude in temperature.
Not, not one order of magnitude, a factor of 3 or something.
Okay. So that,
It has, this jump, if it is available, it has no effect on any, well, applications. But this is a
yeah,
matter of
it's
principle.
academic, yeah.
If it is real or not.
So the solid must develop impurity-like stuff, or it should, behave like an amorphous solid near the transition. There must be lots of ions that are not in lattice sites, and the number of ions not in lattice sites should, have rather smooth behavior for you to approach the liquid.
I would say such, I view it just a little bit differently. I would say that in strongly coupled liquid, on this relaxation times of electrons, it behaves like solid, because it is almost strict order. That is why.
I see. So the Q that is probed in the electron scattering is large.
Yeah. If I may continue, I think I may and I should, I will skip this one. This is just Shell's positive matter. Through the crust and the core, for 3 different temperatures. This is the outer crust, the inner crust, and the core. And you observe, well, this huge jump of shear viscosity. The same will be with the electric conductivity and the thermal conductivity of the electrons. This jump is quite evident because here in the crust we have atomic nuclei which scatter off electrons. They are good scatterers. In the core they disappear. We have no good scatterers for electrons, and there is a huge jump of the transport coefficients.
If I could ask, pasta may live right at that jump. I presume this calculation neglects any pasta.
Absolutely. I absolutely agree this is an open problem. No one calculated the electron thermal conductivity of the pasta phases.
You guess that it will smooth out that jump, right? It kind of interpolates between
It
uniform
will
matter.
be anisotropic there.
Mhm.
It is a complicated thing. And well, I included this as a item which is not solved. Okay, well, I will skip this and this. Well, this I cannot skip because this is the most harmful effect of solid state physics on astrophysics, which I know of if we apply well to neutron star crust. So, before I discuss the cases of one component plasma, so ions have, at each density of the matter there are ions of one type. Yeah, well, there could be multi-component mixtures, that's undoubtedly. And, well, numerous simulations of 2-component free component and multi-component mixtures, and the expert is here, so I hope you will confirm what I will tell. They show that, well, in these mixtures, there is almost always there are almost always regular structures. Well, different ions in multi-component mixtures, they arrange themselves in regular structures. This has been shown, well, long ago. They are not impurities. When we are speaking of impurities, we assume that these impurities, they are distributed randomly over the system. But they are not distributed randomly. They are always regular. So this very well-known formula for the thermal conductivity or electrical conductivity, which contains this impurity parameter and which gives low conductivities of the metal, I am sure that this is wrong. It is, well, it is written in several papers, but not very perhaps well. But the authors perhaps did not insist. But it will be done, I hope, in the nearest future. Someone will, well, just follow the transition from a random distribution of ions to regular distribution of multi-component ion systems. This is also, well, the theory is available in the solid-state physics, and will show that this impurity parameter does not determine the electron or thermal conductivity of the matter at low densities. So it is like this.
Probably depends on how fast you freeze this thing, right? I mean, you know, if it may be what you're saying, I think is likely scenario, that if you take a random mixture of highly correlated ions and give it enough time to form a crystal, it's likely going to form multiple regular structures. But if you freeze it really fast, then you may have a situation in which you have impurities.
It might be so, but how fast?
Yeah, I don't know the answer to that.
Yeah, it might be so, but, well, in computer simulations, all computer simulations, they show quite well that these impurities are not available. Well, these are unsolved problems. A lot of them, I think I should just know, or almost know. Well, so I will skip this. This is, well, the description of the effects of the magnetic field. The magnetic field make the electron conduction anisotropic. So instead of one coefficient of, for instance, thermal conductivity, we will have one tensor quantity which is determined by three coefficients: the conductivity along the magnetic field, across the magnetic field, and the whole conductivity. And so for the electron conduction, and this is the electric resistivity tensor. There is some theory which is not very exact. At high temperatures this theory is correct, at low temperatures it does not solve the problem. And well, all the magnetic fields can be subdivided into non-quantizing magnetic fields, weakly quantizing magnetic fields, and strongly quantizing magnetic fields. Well, I will skip this, This is the structure of electron Landau levels in the magnetic field. So, if we have this situation, when the electron Fermi level is here, so many Landau levels are populated by the electrons, and the width, thermal width of the Landau of this Fermi level is larger than the spacing between the Landau energy levels. So the field is non-quantizing. If the electrons populate many Landau levels, but this temperature is low, so that the thermal width is lower than the spacing between the Landau levels. The field is really quantizing, and if you have this situation when the electrons populate only one ground state Landau level, the magnetic field is strongly quantizing. So if we have the magnetic field of 10 to the 12 Gauss and have this density temperature diagram for iron plasma, we have three regions. This green region is the field of non-quantizing magnetic fields. This red one is the field of strongly quantizing magnetic field when the electrons, well, all the electrons are settled on the ground Landau level and strongly modify the transport properties. And this is the domain of weakly quantizing magnetic field. If we plot, for instance, the electric and thermal conductivities as function of density for different temperatures of the matter, they will oscillate. They are quantum oscillations which are associated with population of different Landau levels. When we grow up, when we increase the chemical potential, new Landau levels will be populated, and these oscillations are associated with this population due to this square root singularities of the density of states of electrons in a magnetic field. You will have huge difference between the electric conductivities across the magnetic field and along the magnetic field. For instance, if we have the thermal conductivity of electrons, the longitudinal conductivity along the magnetic field will behave like this, and across the magnetic field in the field of 10 to the 12 Gauss, it will be here, several orders of magnitude slower. And it oscillates because of quantum effects. Okay, the oscillations of thermal power, and then unsolved problems, too many of them to discuss now. This ion conduction, just a few words about ion conduction. For non-degenerate electrons and rarefied plasma in a magnetic field, the problem was solved by Draginsky many years ago. Well, in the neutron star crust, at not too high densities, for instance, densities around, well, smaller than 10 to the 4, 10 to the 3 grams per centimeter cubic, ions contribute mainly into shear viscosity of the matter. Then ions contribute into the, well, it is important problem to calculate the diffusion coefficients, especially in strongly coupled ion liquid by molecular dynamics. Well, and finally, if we have a plasma in a very strong magnetic field, the electron thermal conductivity will be strongly reduced across the magnetic field. And the ion thermal conductivity then will become competitive, and it is important. Well, I will discuss this. There are unsolved problems, a lot of them. And then heat conduction of neutrons, well, actually the open field on the, well, this conductivity due to superfluid phonons. This problem was solved by Sanjay Reddy and his collaborators. So this, well, the list of unsolved problems is long. Well, the applications, I will show you this, well, list of applications is huge. Well, this kinetic theory is really needed for applications. For the theory of cooling isolated neutron stars, for cooling of magnetars, for studying oscillations of neutron stars, for ohmic decay of magnetic fields, because the crustal magnetic field, it decays, well, strongly, and it produces, well, the amount of heat which can be important for the thermal evolution of all neutron stars. And for many other problems, for pulsar glitches, well, I think there will be a special session about that. So I do not know.
You weren't here last week. It was explained. I will not be talking about that. Refer all such questions to Russell.
Okay. So, this is, well, what to use, where to find. So the databases were created by Sasha Patechin, my colleague, and there is a very good one, this online database, these references here. You can use the subroutines to calculate the transport properties in the crust. And finally, the conclusions are like this. So, perhaps we have some general understanding of the transport properties. I'm sorry, well, I was in a hurry. This should be outer crust. So if we are speaking of the outer crust, we think that we have some understanding of the transport properties, but perhaps this understanding is just an illusion. Then, there is no illusion that we do not know transport properties in the inner crust. There is some understanding which kinetic properties are needed for applications and under which conditions. This is really so on. Running these cooling codes and so on, I know what to calculate. So, and finally, there is a zoo of many well-formulated, unsolved problems of physical kinetics of the neutron star crust. There are plenty of them. They are quite standard problems of physics, and you should not well think what to do. There are very many of them. I'm sorry, this is non-profitable business because, well, it's difficult to calculate, but you perhaps will not gain too much by solving this nice problem. So,
What you're saying is we shouldn't just sit back and wait for you to do it. Everyone should give their new students should be given one of these problems before they work on the profitable stuff.
I don't know how to arrange this. Actually, if you can do it, please.
No, probably
do
not.
it.
Sort of National Neutron Star Service.
Yes, that's right.
So,
You have to spend 1 year.
this is like this. Think of this. His Majesty the King, neutron star physics and physical kinetics grabbing the flow. If this wonderful problems will be solved, I hope that, well, this into the green. So thank you very much. I'm sorry.
At the very least, I think we could demand that the people that are doing profitable neutron star work should dress like that at conferences. I think that's only fair. All right, we certainly have time for questions and more discussion. I think so. Who wants to start?
That floor looks very clean, it's better than usual.
Maybe
Can I go back to the impurity scattering? If you have a very, very low impurity,
Yeah.
then this impurity scattering makes sense. But so although
Absolutely. Absolutely.
and the whole will have amplitude.
Yeah, I perfectly agree. But if we have a very low number density of impurities, this correction to the conductivity will be very low. This Q parameter will be very low. You should take this into account because you obtain these calculations of real impurities with a pair distribution function without this correlation peaks, or this small correlation peaks. That's the question, not to me. Sorry.
Maybe just a comment. The impurity parameter itself is a very nice way to summarize the nuclear reactions and the nuclear physics composition. You want some simple measure of how dirty
Yeah.
the composition is.
Yeah.
Of course, the thermal conductivity is not simply proportional to K.
Yeah. You can calculate, but it does not determine the thermal conductivity or electrical conductivity of the light.
So, given that there's, this is a rather complex problem, obviously, given all the slides that we skipped. Are you worried that in the applications,
Yeah.
we tend to be too naive? Because when you come from that side, you tend to try to think about problems as simplistically as possible. So, for example, the thermal power would be something that many applications you just wouldn't worry about. And so, are you worried that there are much fine detail, fine print, quite a lot of mechanisms and possibilities that we might discover as we go along? Or worried, maybe the wrong word.
Difficult to say, and it depends on the applications. For instance, if you're speaking on cooling of ordinary neutron stars, then Harsh will discuss this. Then, if it is an ordinary neutron star, well, middle-aged, then what we need the thermal conductivity just near the surface, maximum 10 meters under the surface. And it doesn't matter what are these details in the deeper layers. But if, for instance, we consider thermal relaxation of in soft X-ray transients when they go from the active state to the quiescent state, then we need the conductivity just in the inner crust, and there could be surprises there. And in magnetars, that's well, serious problem. It seems to be important to know the thermal conductivity through the whole crust or through the outer crust and the outer part of the inner crust as well. So it depends. This thermal power is just, it is not needed for majority of applications, but if you would like to consider just then at this project of generation of the magnetic field at the early stage of the evolution of neutron stars, then you need this and just in the inner crust. There are many thermomagnetic effects which can operate in young neutron stars which are almost not considered at all.
And I'm just thinking that we have a sort of bias, perhaps, to always try to look at for natural reasons, you start with the simplest thing you can do, but then we keep on being, quote, surprised when we discover, say, the superfluid phonons being perhaps relevant, but if you think about superfluid hydrodynamics, it's obvious that this was going to be important. And so it's just
of course,
whether we, it's just a reminder, I think, that we should always be thinking about that the real system is much more complicated than what we're able to model.
yeah.
And there could be surprises.
Yeah. For instance, bulk viscosity. Bulk viscosity is a crust. It is a metal problem, just general. There is nothing is done. Just this superfluidity in the nuclei, in the inner crust. They are superfluid, they are slightly superconducting. They are superconducting balls which are vibrating in the crystals and they scatter electrons. And this might be some mechanism of electrical resistance. This problem hasn't been considered at all. So there are many of them. I'm sorry, my talk was very turbulent. I could not formulate all these problems properly. Yeah, and I'm sorry for taking the time.
Well, along the lines of, trying to understand impurities, probably a question to Chuck, is when you do a multi-component simulation and you expect to make crystalloids, small regular structures, what about the ones where you have, like, if you have a 1% component of some impurity in the liquid, how does it find time to form its own regular crystal? I mean, the smaller the population of a species, it's more likely to end up as an impurity rather than a regular crystalloid. Right?
Plenty of time, is the short answer.
Sorry?
There's plenty of time. Think of an accretion time. By the time you get down to 10 to the 10 grams per cubic centimeter where it's going to freeze, it could be 1,000 years. And 1,000 years is really, really long for the diffusion or crystallization. So, I mean, I find it can form a regular crystal on timescales that I can actually simulate on molecular dynamics, which is incredibly short compared to this 1,000 years.
So there's nothing like caging. Impurities don't find themselves in some kind of local potential trap they can never get out of.
That's an important point. Think of a hard sphere system. So if you had a hard sphere system with different sized hard spheres, that can form a glass where the hard spheres get stuck. This 1/r, the long-range Coulomb interaction, is very different. And the little impurities, the small z's, diffuse relatively quickly, even in the solid. So there aren't cages.
But aren't the relevant rates the rate of diffusion compared to the nucleation physics? You have some front that's propagating, which is a harder problem to solve, I think, than the nucleation physics. So even if the cooling time's 1 billion years, aren't those the rates to be comparing?
I mean, an accreting neutron star is growing new crystal at the accretion timescale. So I'm not sure that this nucleation front, I'm not sure. So
It's certainly relevant if we're not considering accretion, the formation of the crust to begin with.
Yeah, so an isolated neutron star is a little bit different. You have the cooling timescales from the supernova. But my prejudice is the molecular dynamics is very fast.
I think we're all terrified. I think let's thank Dima for scaring us and have a quick coffee break, okay?
That was my purpose.
So let's resume in 5 minutes or so we can set up the next presentation.
Nice to see you. How have you been?
I'll be